Today we're going to learn about one of the most common distributions, period, and that is the normal distribution. But before we do that, let me show you another favorite distribution, the paranormal distribution. You get it? Paranormal ghost. Anyways, so let's say you roll a die 360 times and plot the results. What would you get? Well, you'd expect to get an equal amount of ones, twos, threes, fours, fives, and sixes. A distribution shows the outcomes and the rough frequencies that you would get them. In this case, each roll is equally likely, and the distribution at right is called a uniform distribution because all the proportions are equal for each outcome. Now, let's say you roll a die 2 times and sum it. In this case, not all the outcomes are equally likely. It's harder to roll a 2 and a 12 than it is a 7. So the most likely outcome here is a 7, and the least likely outcomes are 2 and 12. So we could look at a lot of instances and say, oh, okay, there are different shape distributions out there. Let's go ahead and take a look at the binomial distribution with many rolls. This is a virtual simulation for flipping a coin. So here it shows one flip and the probability distribution for the number of heads. So for one flip, you would guess you'd either get heads, you get 0 heads half the time and 1 head half the time. If I go to 2 flips, then you get 0 heads a quarter of the time. You can see it here. 1 head half the time, 2 heads a quarter of the time. And as I keep increasing it, you can see the number of heads changes based on the number of combinations we can get. And the shape is starting to get a little familiar. In fact, as I keep going up and up and up, what does this look similar to? This looks a lot like the normal distribution. And in fact, when you're doing a binomial distribution, and this is only with 50 flips, it already is looking very much like a normal distribution. Even if I were to bring it down to, say, 25 flips, it would still look very similar to normal distribution right there. So one of the things we can do is we can actually use a normal distribution to flip the coin, to simulate our binomial experiment. Now, there are some conditions on this. If I only have one flip, if I'm only doing one sample, this doesn't look anything like a normal distribution. They basically have a rule that n times p must be greater than 10. So when would that happen? When n is greater than 20. And so I'm sliding n up to 20 here. And that works pretty well. Now, if I lower probability, what's going on with the distribution? It's sliding left. So if I have something as low as 0.05, just a 5%, even if I put a big N here, so 50 times 0.05, if I multiply that out, that would be roughly 5% of 50, 2.5 when I multiplied it out. So that's still too small for the normal distribution. What's going on here is that the normal distribution assumes that you can go on forever to the left. And you can see here with the binomial distribution, the least number of heads you can have is 0. Or in our case, successes that we can have is 0. So as long as this product, let's say, let me raise this up to 0.2, then you can see that I've got most of the normal distribution so that it's visible. And that's a pretty good approximation. So we have a general rule that as long as n times p is greater than 10, that's fine. Now it also goes the other way, because if I jump this all the way over to 1, p times n in this case is 50. It's much greater than 10. But the problem is now everything's succeeding. So as I slide this back, I also want n times q to be greater than 10. And so I have to do both checks. The n times p is greater than 10 and n times q is greater than 10. So where do we see the normal distribution in real life? You can see it a lot in test scores like the SAT score distribution on the left. Heights, you have women and men. You could argue that the men's distribution on the low end is not quite so normal, but generally pretty normally distributed. So because the normal distribution is so common, we know what it looks like if we know the mean and the standard deviation. There are three rules called, these are part of the empirical rule, that gives you a general properties of the distribution. First of all, we know that there's your mean. By the way, we put the mean in the center, so we expect to find that. And you really helps to have this graph drawn. So we expect 68% of the data to be within one standard deviation of this mean. So that means it would be from, if I go, here is one standard deviation below and that's one standard deviation above, I would find 68% of my data there, where this is mu minus a sigma for standard deviation, and this is mu plus sigma for standard deviation. All right, and that, if I split it up, I can say this slice right here has 34% of the data because it's centered about the mean and it's symmetric. And the other slice is going to have 34% of the data. The next rule is that 95% of the data is within two standard deviations of the mean. So if I go down another standard deviation here and up there, I'm going to capture 95% of the data. Now I can actually figure out how big this slice is. For example, I went from 68 to 95%. That is about 27%. And I'm going to have an equal piece on each side. So I'm going to have 13.5% on the left and 13.5% on the right for that green, those green slices reach 13.5%. Now the last one is 99.7% of the data is within three standard deviations of the mean. So here you go, there's 99.7% of the data. And if I figure out the size of this slice, I went from 95 to 99.7. So that would be 4.7% of the data that I added on. And if I divide that by 2, 2.35% for each side. Now, have I covered all the data? No. Off to the left, as far as you can go, is half of what's left over. The leftover data is 0.3%. Half of that is 0.15%. So you're going to find it really handy if you have this drawn and use it for your problems. If you just go ahead and put your mean and then keep adding standard deviations on the right, and if you put the mean and keep subtracting standard deviations on the left, when you're using the empirical rule, it gets pretty easy to calculate percentages of data within certain ranges. Okay, so we're looking at a study investigating the effect of car speed on accident severity. The vehicle speed at impact was recorded for 5,000 fatal accidents. The mean speed was 42 miles per hour and the standard deviation was 12 miles per hour. The model is 42 and 12. We usually list the mean first and the standard deviation second. So if you see notation like that, it means a normal model. So I already have my curve here drawn, but instead of putting mu, I know what mu is, so I can put it down there. It's 42. And then I can go ahead and add 12 to 42, I get 54. Subtract 12, I get 30. Add another 12 here and subtract another 12 and keep going until I have my model filled out. So now when I ask you what percentage of speeds are greater than 42, you might say, oh, I didn't really need the graph because that's pretty much half the data, or 50% are going to be greater than the mean. So when you're looking at 1/2 of the bell curve or normal distribution, you have half the data. All right, what interval of the vehicle speeds for the 68, what is the interval of vehicle speeds for 68% of the data centered around the mean? Well, that's this yellow region right here. So all I have to do is say 30 to 54. 68% of the data is within the interval 30 miles per hour to 54 miles per hour. Now I'm going to ask for 95% of the data. Well, that includes the green, yellow, green, because I'm going 2 standard deviations away from the mean. The mean's 42. 1, 2, 1, 2. So my interval is 18 miles per hour to 66 miles per hour. Now, if I'm looking at 99.7% of the data, I'm going 3 standard deviations out. So the interval would be from 6 miles per hour to 78 miles per hour. Now, what if I asked you what percentage of speeds were between 6 and 30? So here's 6 and there's 30. I'm looking for these two slices. In other words, this piece and that piece. Adding them up, I get 15.85%. So that's the percentage of speeds between 6 and 30 miles per hour. What percentage of speeds were less than 66 miles per hour? So we're looking at data from here all the way down. That means I'm going to include this slice, the yellow section, the green slice there, the purple, and the little piece before it. So adding it up, I'm going to add 13.5 plus 34 plus 34 plus 13.5 plus 2.35 plus 0.15%. And I get 97.5%. Now, because it was so many slices, sometimes there's an easier way to do this. I could look at what I didn't want, which was this piece, and subtract it from 100%. So 100% minus that section, which is 2.5% by the way, gives you the same answer, 97.5%. Now we're going to look at a 1903 study on inheritance. The average height of the mothers was 62.5 inches with a standard deviation of 2.4 inches. So the model is 62.5 and 2.4. First, we're going to put our mean down on our graph and then subtract 2.4 for this number and add 2.4. And we just keep going one more standard deviation out till we go at least 3 standard deviations. They want to know what percentage of people are less than 62.5 inches tall. Well, that's just the lower half. Half or 50% are less than the mean. All right. We'll make it a little, we'll go ahead and find the intervals. If we're doing 95% of the population, according to the rules, that's 2 standard deviations away from the mean. Remember the mean's here, so 1, 2, 57.7, 1, 2, 67.3. So 95% of the data is within the interval 57.7 and 67.3 inches. What if I want the interval for 99.7? That means I'm going 3 standard deviations out, all the way down to 55.3 and up to 69.7. Now I want the percentage of heights between 64.9 and 69.7 inches. Well, what would I do there? I would basically, I know I want this area, and taking the green and the purple, that would basically add up to 15.85%. So I can say about 15.85% of heights are between 64.9 and 69.7 inches. What percentage of heights are greater than 67.3? So I'm looking for this upper area right here. And I can just say, oh, that's what I want. 2.35 plus 0.15 is 2.5%. So 2.5% of the heights are greater than 67.3 inches.